All right, here we go. All right, good afternoon, I guess. This is Mr. Arasena. If you're not watching it this afternoon, then good morning or good evening, depending on when you guys get to it. So welcome to Mr. Arasena's Physics live stream. This will be the first broadcast for, I guess, this semester. I've done this before, but it's the first broadcast for this semester. Kind of appropriate considering what's going on. So my plan for today's live stream is basically to go over the circular motions problem worksheet that was assigned at the end of the applications of circular motions video from Monday. Was it Monday? Yeah, it was Monday. I submitted that, or I posted it. The answers are on the worksheet. Like you can see here, the answers are here and here, but the solutions are not given. So if you attempted the problem and you weren't getting the answers, then hopefully today's video will clarify some of that for you. Okay, this might be quite lengthy because there are 6 problems, and I'm going to be talking quite in depth about going about solving each problem. So hopefully by the end of this, I'll timestamp each specific question. So if you only have a few questions, or if you only have one question that was giving you issues, you can just jump forward to that once the video is done. Okay. If you haven't attempted the problem set yet, then I would highly suggest that you do that first and then come back and watch this video after I have finished going over it. Okay. That way you guys kind of don't cheat yourselves out of trying it yourself and learning that way. Okay. All right. So let's start with the first problem. We have a light string that can support a hanging load of 25 kilograms for braking. The same string was then attached to a 3 kilogram mass on a horizontal frictionless turntable with a radius of 0.8 meters. And problem asks us, what is the maximum speed of the turntable before the mass breaks free from the string? All right, so let's write down a couple of things first. So if I were to hang a mass on the string, the maximum mass it can support is 25 kilograms. By extension, this means then that the maximum force that the string can support is equivalent to the force of gravity of 25 kilograms. So we can say, okay, so the maximum force on this particular string will be the 25 kilograms times g, which is 9.8 newtons per kilogram. I'm going to use the newtons per kilogram for g in this particular problem because this way the kilograms will cancel out, and we are going to be left with a maximum force of, I think, 245, I think. Let's pull up a calculator. So 25 times 9.8, so yeah, 245. So the string can support a maximum of 245 newtons. Okay, that becomes important because in the next part of the problem, it says, okay, we use the same string, we attach it to a 3 kilogram mass on a horizontal frictionless turntable with a radius of 0.8 meters. So let's draw my turntable. There's my turntable. And we attach a string like so, and this is a 3 kilogram mass, so this is 3 kilogram mass here, and we're asked what's the maximum speed of the turntable before the mass breaks free from the string. So what is my maximum velocity, the turntable going around that way? All right, well, we have the maximum force that the string can withstand. And if I analyze the situation, we are traveling in a circle, which means that the string has to provide some kind of centripetal force that way. Now, what's the maximum amount of centrifugal force or centripetal force that the string can provide? Well, that'll be this. So I can just set my centripetal force equivalent to 245 newtons. So that'll be the maximum amount that I can go around, or it can maintain. And as it travels around this, yeah, we'll get to that. Now, from our formulas, we had several different formulas for calculating centripetal force. There was mass times centripetal acceleration, or mass times velocity over radius, or mass times 4 pi squared radius over period squared. Yeah, that's right. Okay. In this particular situation, we don't have any information about its centripetal acceleration, so we probably don't want to use that. And we don't have any information about the period of rotation, so we don't want to use that. So we're going to end up using this formula. All right, we know our maximum centripetal force is 245 newtons, so we'll leave that there. We have a mass of 3 kilograms here. We don't know how fast the turntable is going, but we do know it has a radius of 0.8 meters. All right, calculating all this out, let's see, 245, that's 245. 245 newtons times 0.8 meters, and then we'll divide by the 3 kilograms, divide by 3 kilograms. That'll be equivalent to my velocity squared. All right. Doing the calculation, 245 times 0.8 divided by 3. So our v squared will be 65.33. The units will end up looking Newton meters per kilogram. Odd unit. Squared. And then we just take the square root of both sides. And this will give us second function square root. There we go. Oh, whoops. Why did it divide by 3? Okay. So 65.53 second function square root. There we go. 8.08. And when we do the unit analysis, this will end up with meters per second. There we go. So there is question 1. Now, if at any point any of you guys are watching live and you want to ask a question, just type it into the chat, and there will be a slight delay, so I might not be able to get to it right away, but I will see it, and then we can discuss your question appropriately. All right, question 2. Here we have a coin. We are placing it 30 centimeters from the center of a horizontal turntable, and it starts to slip off when the speed is 50.0 meters per second, or sorry, centimeters per second. 2A asks us, what provides the force towards the center of the turntable when the coin is still on the turntable? So if I draw my thing there, I place my coin. What is keeping it traveling in a circle this way? Well, unlike the previous problem, there's no string attached to the coin, so the coin cannot, well, there's no tension in string, but because it is sitting, and I think, is it mentioned that it's, oh yeah, okay, it's not a frictionless turntable because B is asking us what's the coefficient of friction. So that kind of gives you a clue that the centripetal force here, the only thing causing centripetal force in this situation is the force of friction. Now, if the force of friction cannot provide enough centripetal force, so if this force of friction here ends up being smaller than the necessary centripetal force, then the coin will probably fly off. Okay? That's kind of what the situation is describing. Now, the question asks us for B, so for A, this is friction. Okay. B asks us to calculate the coefficient of friction between the coin and the turntable. So now that we've identified that the force of friction is what's causing the centripetal force, we can write down a few equations. So we know that the force of friction is equivalent to coefficient of friction times normal force, so mu Fn. And we know that we have several different ways to calculate the centripetal force. We can use mass times centripetal acceleration. We can use mass times velocity squared over radius, or we can use mass times 4 pi squared radius over period squared. Okay. We'll decide which centripetal force formula to use in a moment, but for now, let's focus on how to calculate the force of friction. The big assumption we're going to make here is that we're going to assume the turntable is flat. Assume the turntable is flat. Okay, what this allows us to do is it allows us to calculate the normal force as being equivalent to the force of gravity. So if the turntable is flat, the normal force is equivalent to the force of gravity. Sort of view it like, okay, if this is my turntable, on top of my turntable is a coin, then the force of gravity is going this way, and then the normal force is going this way, like that. Now, this allows us then to say, okay, well, if I know my force of gravity is mass times gravity, and I know my normal force is equivalent to the force of gravity, that means in this case, my normal force must be mass times gravity as well. Okay, and now we have an equation for the force of friction, because if I know my normal force is this, I can take the mass times gravity and I can substitute it into here. So therefore, my force of friction is going to be mu times mass times gravity. Okay. Now some of you might be thinking, as you're watching, it's like, well, do I know the mass of the coin? It's not given to me. That's okay. The mass of the coin's not there, so I guess we'll just have to leave it as m in the formula. Okay, and that's perfectly fine. That's perfectly fine. Mass, gravity. All right. Now, we know that my force of friction has to equal the centripetal force. Which of these equations will then be most useful for centripetal force? We don't know centripetal acceleration, so we can ignore that equation, and we don't know period of rotation, or period of revolution, so I can ignore this equation as well. Okay, which means we're probably going to use this one, which makes perfect sense because it tells us that at 50 centimeters per second, so 50 centimeters per second and a radius of, I think, what did I mention, 30? Yeah, 30 centimeters. That's the information given to us in the problem. This is at this speed, the coin starts to slip off. Okay, first things first though, we're going to convert each of these to meters per second, because our G is going to be, we're going to use the standard unit of G, so 9.8 meters per second squared. So we want to convert everything to meters. Okay, there you go. So then we can say, okay, Fc is then going to be mass times v squared over r. Since I know that from way back here, since I know that centripetal force is being caused by friction, I can set these two this equation and this equation equal to each other because they have to be the same according to our analysis earlier. All right, so let's put that in. So force of friction, mu times m times g, must equal centripetal force, which is mass times v squared over r. Now here's something really neat, and I think we hopefully remember this from the lesson on Monday, our previous lesson. What happens to our masses? Our masses end up canceling out. It's quite handy, quite handy. In a lot of cases, the masses cancel out. So even though we didn't know the mass of the coin, it turns out the mass of the coin doesn't actually matter. All right, so mu is mu. G will be 9.8 meters per second squared. Velocity, we calculated, or we converted to 0.5 meters per second. This will be squared. And the radius of our turntable is 30 centimeters, or 0.3 meters. Right, carrying out this calculation, we'll get mu equals 0.50 meters per second squared, divided by 0.3 meters, and again divided by 9.8 meters per second squared. Pull out our calculator, so 0.5 squared divided by 0.3 divided by 9.8, and we get a coefficient of friction of 0.085. 0.0. And coefficient of friction has no units, so we'll just leave it blank as follows. There you go. So the key here is identifying what's causing the friction, or not friction, what's causing the centripetal force. In this case, it's friction. And then using our equations from our study of forces and friction, setting the force of friction equal to some equation, and then deciding what equation to use for centripetal force. And then because we know that these two are the same, we can set both equations equal to each other. Okay. It'll be a common theme in a lot of math, and at least a lot of physics and a lot of math, in that when you look at a problem and analyze it, if two things are the same, then you can just set their formulas equal to each other and work with them that way. Okay. All right. Okay. So I think those two were hopefully kind of straightforward. Let's go to number 3. Number 3 is the banked racetrack problem. So let me just draw the banked racetrack. So here's the banked curve. We are has a radius of 75 meters, and we're banked at an angle of 15 degrees. So let's draw the angle here. That's 15 degrees. And we're asked to find what is the maximum speed the car can go around this corner. All right. So V max equals what? And then the radius is 75 meters. All right, so let me just draw our representation of our car here, and then we'll discuss again the issue at hand. So we know that on this car there is a force of gravity acting this way. Force of gravity. We know that there's going to be some kind of centripetal force pulling it towards the center. Force centripetal. And on top of that, we know that in order for the gravity to be counteracted, there has to be some kind of other upward force going up this way. Now, that other upward force going up that way is actually caused by the normal force, which is going in this direction. Okay, normal force. I'm not going to bother drawing in the sliding and compressing components here, because unlike a normal inclined plane problem where the car's not moving, the F compressing is not going to be the same as the normal force in this case, because the normal force has to do two jobs. Normal force has to counterbalance the compressing force, and it also has to provide the centripetal force. Okay, so in this case, my centripetal force is part of normal force, and that part happens to be this x component here. So that's the component of normal force. Now when we do the analysis of the angles, it turns out that this angle here is the same as the angle down here. So if the angle here is theta, doing some analysis, the angle up here is also theta. Okay. All right. Now, let's do some calculations. So this upward component here is an upward force, and it has to balance the force of gravity down here. Okay, just using standard force body diagrams. If I calculate this downward force, I need an equivalent amount of upward force to counterbalance it. Otherwise, the object will be moving either up or down, and we don't want that. So this upward force here has to be the force of gravity. Now, this portion here, because the centripetal force and the force of gravity are at right angles to each other, this will form a right angle triangle, and then we can use trig to figure out what the normal force is or what the centripetal force is. Okay, it turns out we don't actually, well, we can calculate the normal force as using SOHCAHTOA, although we'll use the cosine portion, so we can say cosine theta, it's going to be the adjacent side, which is force of gravity, over the hypotenuse side, which is the normal force, like so. All right. Now, With this, we can then calculate the normal force as the force of gravity divided by cos theta. All right, there we go. All right, carrying this on then, we have the normal force is going to be mass times gravity divided by cos theta, because force of gravity is mass times gravity. And if we want to do, we can put in some numbers. So we'll just go m 9.8 over cosine 15, and that's my normal force. We still don't know what the mass of the car is, but you guys can probably guess that the mass of the car doesn't matter and will probably cancel out at some point. So there's my normal force. Okay. There's my normal force. Now, yeah, we're gonna ignore friction, yeah. All right, so then centripetal force. So here's centripetal force. Our centripetal force is going to be equivalent to, if I use SOHCAHTOA, the centripetal force, so SOHCAHTOA, sine. So sine theta will then be opposite over adjacent, so FC over Fn, which means that FC is going to be Fn times sine theta, okay? And the other thing we also know is that FC also has to equal, so my centripetal force also has to equal mass times v squared over r, like so. All right, since both of these are the same, we can set this equation equal to this equation. So we go Fn sine theta equals mv squared over r. And then we can probably do a little bit of simplification. We know Fn from back here. There's Fn. Fn is just going to be mass times 9.8 over cosine 15. Sine theta is going to be sine 15. And here we get mass times velocity squared. And we have a radius of 75 meters. All right. Now, as you can see here, the equations show us that the mass of the vehicle doesn't matter. It gets canceled out regardless. So it can be as small or as big as you want. It doesn't matter. It'll get canceled out. The sine 15 over cosine 15 can be simplified to tangent, tan 15. And then we get the following, v squared over 75 meters. All right, bringing the 75 over, we'll go 75 times 9.8 times tan 15. That'll get me v squared. And if I square root all of this, that'll get me v. So let's carry out that calculation. Over so you can see what I'm doing. All right, so we are going to first clear all that. So 7.5 times 9.8 times 15. Sorry, this is how it gets done on this calculator. There we go. Tan 15. So that's the answer there. And then we'll equal that, and then we'll square root that answer. Yep. And we get the following angle of, or sorry. Oh geez, okay, that's terrible. It's this one. There we go. Okay, so we'll square root the 19.69427 just to make sure I'm keeping enough significant figures. There you go. Maximum speed of 4.4. I think. Oh, whoops, that's not right. It should be 14. Did I mess something up? Let's see. Oh, that's why. It multiplied it by something? No. I multiplied by 7.5. Should be multiplied by 75. All right, let's try it again. So 75 times 9.8 times tan 15. There we go. All right, so 0.26, and then can I? No, that's not. Okay. Okay, 75 times 9.8 times tangent of 15. That equals 196.94. I could have figured that out actually, not in hindsight. And then we'll take the square root of that answer. And there you go. There's our 14.03. probably 14.0 is probably better. There we go. Oh, and then units meters per second. There we go. Yeah, 14. Actually, if proper signifigs would just be 14. Proper signifigs would be 14 meters per second. All right. Okay. So that does it for that one. I might go over tomorrow. I might go over a bank problem like this where friction forces do matter. It's kind of fun, and it does take a lot of bookkeeping though. So, but I might do that tomorrow. All right. On to question 4. Question 4 is actually a little misleading because the diagram doesn't accurately represent what I intended. So here, Spider-Man swinging around the building in a circular path of a radius of 30 meters. He travels around the building with a speed of 18 meters per second. So this is actually treated very similarly to the first question. So the intent was actually basically to illustrate the problem like this. So there's Spider-Man represented by a block, and he's going around a circular path like so. And let's see, the measurements we are given. He has a mass of 65 kilograms. The radius of travel is 30 meters, and he's traveling at 18 meters per second. So radius equals 30 meters, and he's traveling at 18 meters per second. Yes, okay. And the question asks us what is the maximum tension in his webs if he's traveling this way. Okay, the picture is misleading because it seems like he's at an angle, but I'm not gonna do this problem that way. Maybe I'll do that tomorrow as an extension of this particular problem. All right, so what causes the centripetal force in this question? It'll be the tension in the string. So all we really need to do is just calculate what the centripetal force is, and that'll be its tension. We have, I think, enough information to use this particular formula, mv squared over r. Because we have the velocity, we have the radius, we have Spider-Man's mass. So we'll just throw that all into our calculator. 18.0 over 30. Oh, we got to square the 18. There we go. Yeah. Okay, so 65 times 18 squared divided by 30. So maximum amount of tension in his string is 702 newtons, which is actually not the answer I wrote down. So this is actually not correct. 702. Unless I missed something in my calculation. Let me just check. So 65 times 18 squared divided by 30. 65 times 18 times 18 divided by 30. Yep, no, that's right. That's right. So my original answer was wrong. I must have done something different. Anyways, but there we go. So the answer for question 4 is actually this much. So that's the maximum amount of tension that his web lines can maintain. Okay. All right. On to question 5. So question 5 has us building a spaceship in a circle with a radius of 120 meters. How fast must the space station rotate in order for the occupants to experience Earth-like gravity? Earth-like gravity being 9.8 meters per second squared, or 9.8 newtons per kilogram. All right, let's do this. So here is my space station. I'm gonna put a person on that space station like so, and we want this person to experience a centripetal force equivalent to the force of gravity. Okay. All right. We have a radius of the space. It's a very small space station, only 120 meter radius, and that's all the information we have. All right. Well, so we're looking for speed, right? Yes, we're looking for speed. Yeah. Okay, so v equals unknown. So we can say the following. Okay, so fc, we're probably going to use this formula mv squared over r. And because I want fc to equal mg, we can say, okay, this has to equal mass times gravity. Now, again, notice the masses will cancel out during this calculation, which is important because if the spaceship rotation depended on the person on the space station, then not everybody would be feeling the same amount of gravity or the same amount of centripetal force, which is not true. All right. Then we want to calculate for v, so we'll go v squared equals g times r. And if I square root both sides, I will get the following. V equals g times r, all under the square root. We want the gravity to reflect Earth gravity, and we have a radius of 120 meters. Doing our calculation, we now get 9.8 times 120, and then we'll square root that, so 34.3 meters per second. Okay, so that's the speed that you'd have to spin the space station at. Now, this speed, if you remember my example from the other day, is actually the kind of the tangential speed of the person. So this would be the speed of the person flying in this direction. And sometimes that's okay, but to give better context, we want to calculate the rotations per minute. Okay. So to convert our linear speed, so this is kind of like our tangential linear speed. Tangential linear speed. If you want to convert that to a revolution, sort of a revolutions per minute or revolutions per second, we can do the following. Okay. So to change to revolutions per second, simply calculate the circumference. Oops, not calculate, to calculate the circumference. And then we'll divide by the, we'll use that to divide the linear speed, and it'll give us revolutions per second. So the circumference, is 2 pi r. So this would be 2 times pi times 120. So the circumference is approximately 240 pi. Okay, I'm going to leave my answer in 240 pi for now. It's a holdover from my math training. I like leaving answers in pi. It just makes the answer a lot nicer. Okay, and then to calculate revolutions per second, so revolutions per second, we can take our circumference. So this is 1 revolution. That kind of be like our distance. And we can do the following. So we take our revolutions per second, RPS will be our velocity. Right. No, circumference divided by our velocity. Whoops. Go. Okay, so then this will be 240 pi divided by our velocity of 34.3 meters per second. So this is 1 revolution. Oh wait, that's not right. My dimensional analysis is wrong. It should be velocity per circumference. There we go. Because then my dimensional analysis will show the following: 34.3 meters per second over top of 240 pi meters per revolution. And then when I do the division, you get 34.3 divided by 240 equals 0.143143 over pi revolutions per second. And then if you want to go revolutions per minute, let's multiply this number by 60. So RPMs, we'll take this number. So our revolutions per second times 60. So that'll be times 60, 8.575. 8.575 over pi RPMs. Obviously, at this point, the pi doesn't make any sense. So let's just give us a numerical approximation. So we'll divide by pi. So there's about 2.8, 2.7 revolutions per minute. So that kind of gives you a better idea of just how quickly it's spinning. The 34.3 meters per second seems really fast. That's over 100 kilometers per hour. But you don't really get a full sense, at least I don't think you do, until you go into the revolutions per minute. Then you can see, oh, this space station is spinning 2.7 times per minute, or 2.7 full revolutions per minute. So that's pretty fast for spinning. If you're not used to it, you'll probably get quite nauseated by it. Okay. By contrast, like the space station problem we did on Monday on the other lesson had a speed of close to 1,000 kilometers per hour, but its actual rotations per minute were quite small. So large linear speed, but slow actual rotation. Whereas this one had a relatively small linear speed, but because of the size of the spaceship, the rotations are actually quite fast. And you probably don't want a spaceship spinning this fast, or a space station spinning that fast. It'll make everybody nauseated on board. All right. Okay, last problem here. We have participants of a roller coaster go through a loop, and we want to calculate normal force at the top of the loop and normal force at the bottom of the loop. This just requires some interesting force diagram analysis, and 6a kind of directs you towards doing that. So 6a forces causing the centripetal force at the top of the loop. So let's draw the top of the loop. So let's say top. So here's the top of the loop. Okay. There is the roller coaster. Okay, and we want to know what are the forces acting on this person. Well, we have force of gravity acting on the person. We've got, now in this case, the normal force is actually acting this way. There's the normal force of the person. And then finally, we've got centripetal force going this way. Okay, so the centripetal force at the top of the loop looks like it's going to be the sum of the force of gravity and the normal force, like that. Okay, so that's what the forces look like at the top of the loop. At the bottom of the loop, and actually that's for this type of roller coaster, for that type of roller coaster. At the bottom of the loop, so if I'm going at the bottom, or even like a dip. So here's our person. We have the same thing, kind of. We have force of gravity going down. We've got normal force going up. And then my centripetal force, my overall centripetal force is actually going to be going up like that. Overall centripetal force. And you sort of see here that the centripetal force is going to be the normal force minus the force of gravity. Because in the bottom, the gravity and the normal force are opposing each other. Whereas at the top of the loop, the gravity and the normal force are going in the same direction. So they're adding together to create the centripetal force. Okay. So there's the force analysis at the top and at the bottom of the loop. Now, what are the forces? Well, Or what's the normal force? Well, the normal force, we simply just rearrange this equation to solve for normal force. So here, normal force is going to be centripetal force minus the force of gravity. That kind of makes sense because the centripetal force is acting with gravity to create the centripetal force. And at the bottom here, the normal force is the centripetal force plus the force of gravity. And when we think about it, that should also make sense because the normal force, in this case, is actually counteracting gravity while at the same time needs to provide enough centripetal force to keep the object moving, or to keep the object moving on the centripetal path. Right. Plugging in some equations, we can see, okay, my centripetal force is going to be mass times velocity squared over r minus the force of gravity, which is just mg. And then here, same thing, force centripetal is going to be mv squared over r, but this time we're going to add the force of gravity here. Now, you can actually experience this. I think I mentioned this before break. You can actually experience this increased normal force anytime you are driving really fast into a valley, into a dip in the highway. Because as you get to the bottom of that dip, you should feel yourself a little heavier because as you're coming out, your seat should exert more normal force on you as you go up the hill. Here, even if you are kind of like this, the normal force is still kind of going to act the same way, in that as you are skirting over the top, depending on how fast you're going, the normal force, you'll feel a little less normal force as you go over top as you go over top of the crest of the hill, or the crest of the loop. There you go. All right, so with that goes through the entire solution for this problem set. We'll probably start talking about gravity in the next video, and we'll talk about not just regular gravity, because we've already talked about regular gravity, F equals mg. No, we're going to talk about universal gravitation in the next lesson. Okay. All right. Again, if you guys have any questions, you guys all know how to contact me, and we'll see you guys next time.